Welcome to the section 3.8 pre-class video assignment. In this section, we're going to look at modeling a system of differential equations, second order, in this case where the forcing function is a force delivered by an impulse. So an impulse would be, again, a large force delivered over a very short time interval. So think of this as, again, it's convenient here to think of, again, we've seen the second order situation, a mass spring system. Imagine a mass spring system which is oscillating, and then at some moment in time, we go ahead and smack it with a hammer. So this would be like an impulse. So in order to define this situation, model this situation, we define something called the unit impulse function. So the unit impulse function also has a, again, it's denoted delta sub A. Delta sub A of t minus t0. Basically, this is going to model an impact at time t0. So the delta sub A unit impulse function is a piecewise function. It is basically zero everywhere, except for a very short interval in theory where it is equal to 1 over TA. The interval itself also has a length of 2A. So basically, this is what the A here is referring to. We have an impulse. We have an impulse sort of centered at time t0, and then the length of the impulse starts at t0 minus a and lasts until t0 plus a. So again, in theory, this is a very short time, but again, the interval here is a length of 2a. Hence, if you look at this guy here, we have a length of 2a and a height of 1 over 2a. Therefore, the total area, if we were to integrate from 0 to infinity over a unit impulse function, we get a total area of 1, hence the term unit impulse. So this situation here is not really a calculus situation. It is modeling an actual impulse that lasts for a short period of finite time that we know of. Modeling, we want to really do better than this. We want to really have this idea of sort of a idealized or generalized impulse. And this is sort of your perfect idealized impulse is one moment in time. So when we look at something like, try to model something like this, we actually get what's called the Dirac delta function, which is something that we're going to be using in this section. Basically then, the Dirac delta function, which is just delta, not delta sub A, is the limit as A goes to 0 of the unit impulse function. So notice what happens here. So this is kind of what this picture is trying to illustrate. If we start with an interval 2a wide, but if a is 2a wide, then it would be 1 over 2a tall. If we shorten that interval, then the height of that function will become 1 over 2a, would have to become taller, and so on and so on. So as a goes to 0, we get a skinnier and skinnier impact interval, but by necessity, the magnitude of this function would have to grow to maintain a unit impulse underneath. So the limit of this process is called the Dirac delta function. It must be a situation as follows. That is, it has these following properties. As a goes to 0, basically the height of this curve here must go to infinity. It is going to be 0 everywhere else. And again, it is still meant to be an impulse, a unit impulse, so it still has a magnitude of 1. So these are basically the properties that define this function. So this would probably look a little strange. We call it a Dirac delta function. It's probably got some issues in terms of precise definitions that we've learned in algebra as far as being a function goes. But again, we simply are going to imagine that we have this function that has these properties. One, it is basically an infinite strike at, it is a unit impulse delivered over an infinitesimally small interval, hence being having a height here that goes to infinity. Then notice we can, most books just include these two properties. I've thrown in this as a third property. This hopefully is fairly obvious, probably why books don't usually put it in there. But the point would be is I can then model an impulse of whatever magnitude I would like. It doesn't have to be an impulse of a single unit force of whatever that is. We can multiply by k to get an impulse of whatever magnitude we would like. So this is the unit impulse. This is the Dirac delta function. And again, this is the thing that we're going to be working with here. This is what we use to model an impulse at a moment t0. So let me go to another little document here just to illustrate something here. Again, so in a previous section, we were using unit step functions to model a forcing function where we have forces that could be switched on and off or even ramped up. In this section, we are modeling, again, a different situation where we have one impact. We're going to model we could model multiple impact, but again, the Dirac delta function models an impact or an impulse that is delivered to our system. Again, so I like to think of this as a mass spring system that is oscillating, which you then hit with a hammer at some moment, up or down. And again, this is what we're going to model by the Dirac delta function. Again, this is a rather strange function, I guess function in quotation marks perhaps, but it does work for our purposes here. And again, a Dirac delta function, delta t minus a, this is a unit impact that occurs at time t equals a. So notice then we can model different types of impacts. So just for example, hopefully this is fairly easy to understand, that 0.1 delta t minus 3 is a pretty small impact that occurs at time t equals 3. 100 delta t minus 7 would seem to be a relatively large impact that occurs at time t equals 7. Notice that impacts can be in an upward or a downward direction. So 5 delta t minus 2 would be an impulse of magnitude 5 delivered in an upward direction. Minus 5 delta t minus 2 is the same magnitude impulse, but delivered in the downward direction. And again, remember, we are using the convention that the positive direction is up and the downward direction is negative. Again, not all books do it that way. All right, so here's three little examples to try. These are conceptual. These are matching graph questions. You want to think about the direction of an impact and the moment in which it happens in order to match these graphs up. So give these a go. First one. And there's a second one to try. And there's a third matching graph question to try, so look at those. Okay, so back to the notes for a little bit here. All right, so once we have this idea, clearly in order to solve initial value problems for second order DEs with forcing functions that could include impulses, obviously what we need is to be able to come up with the Laplace transform of this Dirac delta function. So this is the result here. The Laplace transform of delta t minus t0 is e to the minus s t0. This is how it's written in the book. So fairly simple result. T0 is a minus e to the minus st0. So in order to prove this, and again, you won't need to reprove this, but if you're interested here, the way to prove this is first, we start with the unit impulse function delta sub a, and we can write this in terms of unit step functions. So it is the function that is 0 everywhere, but at time t sub 0 minus a, it turns on at 1 over 2a, and then at t 0 equals plus a, or excuse me, at t equals t0 plus a, it turns back off again. So we're subtracting 1 over 2a again. So if we write this if we write this unit impulse function in terms of unit step functions, we then know how to do Laplace transform of unit step. So again, that's what I have here. I have applied what we learned about Laplace transforms of unit step functions. So we're applying it here, and then this is what we would get here. So again, remember that information from last time. So the only thing, well, we can work on that a little bit. So I have simplified this a little bit. You can apply exponent notation here, factor out an e to the minus st0, and get something that looks like this. So this is where I end up here, sort of working on this and simplifying. Then, in order to get the Laplace transform of the Dirac delta function, we simply need to take the limit as a goes to 0, right? This is how we turn our unit impulse into Dirac delta. So we're doing the limit as a goes to 0 of this function. And if you work this out, this ends up being our result, e to the minus st0. If you want to see the work for this limit, that is a L'Hopital's limit derivative. So you can use L'Hopital's rule to sort this out. So this is the result that you get. Laplace transform of the Dirac delta function, delta t minus t0, is e to the minus st0. So a couple of examples here. Well, what is the limit of the basic Dirac delta function at time t equals 0? Again, this means delta of t minus t0. So this is our t0 time. This is our t0 equals 0. So plugging that into the result here, we get e to the 0, which is 1. So the Laplace transform of the basic Dirac delta function at time 0 is 1. The next one also fairly easy. The function is rather strange. It's something to get your head around, but it actually works out fairly easily. All right, so here's another one here. What is the Laplace transform of this? So here we've got a linear combination of functions here. We've got 2 of them, Dirac delta, one of them is not. Again, linearity of Laplace transform, we can take the Laplace transform term by term. We can move the constants outside. The Laplace transform of e to the t. Well, this is not Dirac delta. This is just from our Laplace table number 11, I believe. Then 4 times this guy here. Well, this is t0 is 2. So this would be e to the minus s times 2, or e to the minus 2s. And then this one here, Dirac delta function of t minus 5, this would be e to the minus 5s. So we just add those together, and this is what we get. Again, so not actually all that difficult. Here's a little MyOpen math problem to try some of those. All right, so that's where we'll leave it for the notes today. We will finish the packet off together in class. Before we go, a little bit more for prerequisites here. We have, again, if there's anything tricky that happens here, it's often with these inverse Laplace transforms we need to take. So if you think about the situation we have here, we're delivering an impulse to a system. Yes, so again, imagine a mass spring system oscillating, and then at some moment we smack it with a hammer. So what I would expect just logically from this is that our solution to a system like this, where an impulse is delivered, needs to be a piecewise function. We need to get a piecewise answer here because the function and the mass spring system is behaving differently before the impact versus after the impact. There are two different functions here. This feels like it should be piecewise. So in terms of a Laplace transform, it basically means that this type of problem ends up here. It's going to end up having to do an a Laplace inverse of something like this. Because this is the sort of thing that ends up being piecewise. So it ends up having to do this sort of situation. So we have talked about, so you might want to go look back, but we have talked about how to invert. This is the second translation theorem, the first part of the theorem. This is the one that's convenient for inverting. So you want to practice inverting this sort of thing. So here are a few to practice on. First the first one, and a second one to try, and then a third one to try. And that will be it for today. So that's the end of that pre-class video assignment, and we will finish the packet up in class together. Thank you.